Okay, folks, it's time to play everybody's favorite quiz show, Polar or Non-Polar. Okay, so what does polar mean for a molecule? Here's a little reminder. You learned in Earth science, the Earth has a magnetic field. That means the Earth has a North Pole and a South Pole. The Earth is different on each end. The Earth is polar. It's different on each end in terms of its magnetic field. Earlier this year, we learned that water molecules, H2O molecules, have an uneven distribution of electrons. Water molecules are a little bit positive here and slightly negative on the oxygen side. So overall, water, we would say, is a polar molecule. It's got kind of a negative end and kind of a positive end. That's what polar means for a molecule, an uneven distribution of electrons, so it has kind of a negative end and kind of a positive end. All right, we're going to quiz you and help you learn how to tell if certain molecules are polar or nonpolar just by looking at their Lewis dot diagrams. Here we go. H2, hydrogen gas, polar or nonpolar? Hit pause if you need to think about it. Look at the shape. Look for any extra electrons. Hydrogen gas is nonpolar. H2 is nonpolar. Why? You've got two atoms of the exact same element. They have the same electronegativity. So they're sharing electrons equally because their electronegativity is the same. You could also look at it this way. H2 in its structure has more than one axis of symmetry. There are multiple ways to fold it equally. So we would say that overall it's nonpolar because it has a symmetrical shape and distribution of electrons. Hydrogen gas is nonpolar. Now, each of these explanations is valid. Each of these is interconnected in terms of its meaning and concept with the other explanations, but you should use whatever explanation makes the most sense to your brain. Each of these molecules that we go through. Okay, HCl. Look at the shape. Look for any extra electrons. Is it polar or non-polar? HCl is polar. Here's why. The electronegativity difference. Hydrogen has a low electronegativity. Chlorine has a pretty high electronegativity. So the electronegativity numbers are lopsided. Okay? That means that we've got a dipole. The chlorine is pulling all the electrons towards it. It even has these extra pairs of electrons here. So we got lots of electrons on one side of this molecule. This symbol means a dipole. Positive on this end, negative on this end. Partially positive here, partially negative here. If we look for an axis of symmetry, there's just one way to fold this molecule. That means it's asymmetrical overall in terms of its shape and its distribution of electrons. Polar molecules are always asymmetrical in terms of their shape and distribution of electrons. Polar molecules will always have only one possible axis of symmetry, one way to fold. And again, all these explanations are valid. They're all interconnected and related to each other. Go with whichever one makes most sense to your brain. Okay, HBr. HBr, hydrogen bromide, is it polar or nonpolar? Look at the shape. Look for any extra electrons anywhere. It's going to be polar, just like HCl. We've got a difference in electronegativity. The electronegativity is lopsided. That means that we've got lots of electrons being pulled over here to the bromine and not so many electrons over here. So it's kind of positive on this end, negative on this end in terms of its dipole. And it's got only one axis of symmetry, one way to fold it. That means it's asymmetrical in terms of its shape and distribution of electrons. So this is a polar molecule. Cl2, chlorine gas. Is it polar or nonpolar? Look at the shape. Look at the electrons. Okay, it's going to be nonpolar. We've got two atoms with the exact same electronegativity. So they're sharing electrons equally between these two atoms. Just one bond in this molecule. So it's a nonpolar bond and a nonpolar molecule. It's got more than one axis of symmetry. There are multiple ways to fold this equally. Overall, it's got a symmetrical shape and a symmetrical distribution of electrons. Oxygen gas. Oxygen is a classic example of a double-bonded diatomic element. You have to have this double bond here for each oxygen to have 8 valence electrons. But is it polar or nonpolar? Look at the shape, look at the electrons. Oxygen gas is nonpolar. The electronegativity numbers of these two atoms are the same. It's the same element. So the electrons are equally shared and distributed. And we got more than one axis of symmetry, multiple ways to fold it. So it's going to have a symmetrical shape and symmetrical distribution of electrons. Oxygen is a nonpolar molecule. Nitrogen gas. Nitrogen is a classic triple bond example. We have to have 3 bonds here in order for each nitrogen to have 8 valence electrons. But is it polar or nonpolar? Well, nitrogen is going to be nonpolar. N2 is nonpolar. 2 atoms with the same electronegativity. They share their electrons equally. We can draw multiple lines of symmetry. That means overall this molecule has a symmetrical shape and symmetrical distribution of electrons, so it is nonpolar. CO2. CO2, is it polar or nonpolar? Look at the shape. Look at where the electrons are. CO2 is nonpolar. Okay? We've got electronegativity numbers that are balanced out. The higher oxygens are on either side of the carbon that's a little bit lower. So we've got 2 dipoles that balance each other out. We've got electrons being pulled over towards this oxygen, electrons being pulled over towards this oxygen. The electrons and the dipoles balance each other out. We've got more than one possible axis of symmetry, multiple ways to fold this. So it's got a symmetrical shape and a symmetrical distribution of electrons. The electrons are pulled towards either end, so it's nonpolar. It is the same at either end. H2O, is it polar or nonpolar? Look at the shape, look at where the electrons are. H2O, classic polar molecule. Okay? Oxygen has a higher electronegativity. Hydrogens have a lower electronegativity. We've got lopsided electronegativity. That means that we've got a dipole like this. All the electrons are being pulled over towards the oxygen. We've got these pairs of electrons on the oxygen. Lots of electrons and negativity on one side of the molecule, more positive over here. And we've only got one axis of symmetry. So we've got an asymmetrical molecule in terms of its shape and its distribution of electrons. H2O is a polar molecule. CH4, or methane. CH4, is it polar or nonpolar? Look at the shape, look at the electrons. CH4 is nonpolar. We've got a carbon in the middle with a slightly higher electronegativity. All these hydrogens all around have a lower electronegativity, just a little bit. So we've got 4 dipoles. The electrons are being slightly pulled towards the middle because carbon is a little more electronegative. So those 4 dipoles balance each other out. The electrons balance each other out. They're being pulled towards the carbon in the middle from every direction. And we can draw multiple lines of symmetry. It's got more than one axis of symmetry. So it's got a symmetrical shape and distribution of electrons overall. Okay, methyl fluoride, CH3F. Methyl fluoride, is it polar or nonpolar? Well, this is going to be a polar molecule. The electronegativity numbers are lopsided. Fluorine is the highest electronegativity of anything. Carbon is pretty low. Hydrogen is even lower. So the dipoles do not balance out. All the electrons are being pulled towards the fluorine, from the carbon to the fluorine, from the hydrogens towards the carbons towards the fluorine. Lots of electrons on this side, and only one axis of symmetry, only one way to fold this molecule. So it's got an asymmetrical shape and distribution of electrons. Okay, I'm going to pause right here for a moment, and I'll be right back.